And I want to comment a little bit more. So your red line is basically can be like an intermediate, whether it's a reactive intermediate or intermediate state. But basically, if you get to here, right? So how does it come from? Okay, we talked about aldol reactions last time was a Robinson annulation, right? So then you can look at where you're going to see certain connectivities or rays. So again, the retrosynthetic analysis typically seen with these two arrows. So there might be a question of retrosynthetic analysis on the exam. And basically what you're looking at is if you have a molecule, what is it that you're breaking to get certain transformations. Basically just simplifying it. So in this case we need these two to get eventually into that particular case. So another case, these are basically called transforms. Then classes of transforms are something that looks like this, for example. An ester. Okay, everybody's got the homework? And so again, so just look for every time, and not only on the ones that I'm writing, right? So every time that we're looking at different reaction mechanisms, for instance, the click reaction, right? So what are your connectivities? Where is it that you need to break to get a Z, right? So an N3 minus, and your alkyne or your alkene or whatever might be the case. In this particular case, if you're forming a 6-member ring, and it doesn't have to be necessarily a 6-member ring, it could be other types of structure, but it starts coming from Diels-Alder type of reactions. 4+2 cycloaddition. So where is it that you are breaking? Which ones are you breaking? Which ones are you forming? Of course, these are the synthesis in this particular case. These are just some examples that I show in the case. This is structurally simplifying. This is structurally non-simplifying. So basically, what this is that in this particular, there are instances. So in this instance, this could be seen as you get a compound that's more simple, right? So there is like less functionality, or in this case, you have two molecules. In this case, you only have one molecule. Now, in this particular case, for instance, it's non-simplifying in the sense that in this particular case, you went from an ester, basically hydrolysis or reduction to the alcohol. So this could be seen as a more complex structure. So there are the two different aspects that you can think about when you're thinking about retrosynthetic analysis. You start either with something more complex and you simplify it. You start with something more simple and then it gets more complex. Right? So you have to start or to think about both of these possibilities in this case. Right? And so and these more in-depth explanations you can find definitely on the Smith book. Again, I'll just show some of the examples here, just to illustrate. In this particular case, it's called structurally complicating. So you go upon a particular process, you go to a more complicated structure. So in this particular case, you're actually adding functionality.
Is there a double bond?
No double bond, no. Okay. So in this particular case, what this tells you is that if you have something like this could potentially come from a reduction reaction. And then, of course, later on, like if you wanted to form something like this, how would you get to something like this that we know? What would be the syntax in this particular case to get to an alkene that we know? So, for instance, if you wanted to do, for instance, what do we know to make an alkene in a ring? Yes, just draw. So you can just do RCN, ring-closing metathesis. Right, and then you get your open structure. This was the outcome. And then how do you get the alkene, that right? Then you get the idea here was that you get a more complicated structure or more complicated is because you're actually adding hydrogens. Right? In this case, it's reduced, you have the double bond.
Are those both alcohols on the right?
There's one in OR.
OH, 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 OH.
Okay.
Yes. Okay, so I think I'm gonna skip a few of these transform-based and structural codes. For one that I definitely need to cover that I'm basically going to ignore throughout this course is stereochemical implications. But so far the transformation here is an epoxide, where it becomes more complex, and more often the case is that you're incorporating these stereocenters, right? So how do you make it so that an epoxide has a particular stereochemistry? So as you have seen, kind of so far I've been asking you or telling you to skip stereochemistry in the problems that I found out, or on the problems and on the papers. So I'm not going to comment too much on stereochemistry, but just know that this is something, of course, that it's a concern. It requires more building models or drawing models on the paper so that you can explain or get to certain stereochemical aspects. Right? But that's something that I'm going to just skip altogether. So I'm not going to talk too much in general about stereochemistry throughout the course, right? But just keep in mind that that's incredibly important, and then oftentimes is the limiting factor. If you can get to the right stereoisomer or the stereoisomer that you want, then this, if it is a drug, right, this could be the wrong stereoisomer, this could have effects, adverse effects in your health, versus having the right stereoisomer, but it's getting the right target. Are there any questions? This, I'm not going to test you too much on this. This is just to emphasize the transformations. Okay. Yeah. Well, the one thing that I think is important to know, if you guys don't already know it, is that we have linear synthesis, and you probably see something like this in some way or another. So in this case, if you go A, B, C, D, and target. So this is basically 5 steps, 1, 2, 3, 4, 5. If each step is at 90% yield, so 5 steps at 90% yield each, the overall yield is 59%. And then the way you do is 9 times 9 times 9 times 9 times 9, right? So So 9 times 9 is 81, so then after this three step will be 81%. Right? If this is also 90% yield is 8 times 9, so it becomes 72%. It's 7 times 9. Then you get the idea. Is that clear? You guys know that? How to determine those pretty quick. Right? So if you have a two-step synthesis, so you're going from A to C. If this step is 90 and this step is 90, then your overall yield is 80%. That's what there is. That's right, so use times. That's it. Okay, so that's a linear synthesis. We have convergent synthesis. Yeah, I don't know. A, B, C, D, E. K, you combine these two, you get K. Go to your target. And so in this particular case, you want to get to your target, you break the molecule in two, and this is basically the what you get here. So in this case, it's 10 steps, at 90% yield each. So this is basically you go to the lowest linear route of, in this particular case, 6 steps, 0.9 6 plus 53%. Right, so in these particular cases, the way a yield is often determined, the way you would pick is you go to the lowest linear route. Right, in this particular case. 1, 2, 3, 4, 5, 6. Supposed to be the other one. First, you just go to the lower one. Does that make sense? So that's just a couple of things. So that's then we have multiply convergent. And this also goes back to strategizing, right? So in a strategy, when you have a particular target, you can do a linear route, or you can just break your molecule, such as the case in a Diels-Alder reaction. If you break your molecule, that will decay, and then you get both of your diene or dienophile separate. Right? That would be the example of a convergent synthesis. You also have multiply convergent. In this particular case, A to B to C, B to E, F, L, H, I, H, K, M, and combine these to get to your target. Right, so in this particular case, 10 steps, 90% yield. The lowest route of, in this case, 4 steps. That's lowest linear route, 4 step, 66%. Right, so 9 times 9 times 9 times 9. So again, in this particular case, just want to emphasize the strategy that if you have a target, you break it, then you can break both of your intermediates, right, to different steps. So that's, for the most part, multiply convergent, the strategies on how you can get to a particular structure. All right. So, for instance, you have something like this. Orange, more, So for this particular case, so what is the immediate breaking point? So that would be a clear point in this particular case. So what would you use? Would you use a convergent synthesis, right? Linear synthesis? What would be the easiest? If you want to get to simplify the structure, right? So to get to the most simple. So what are the places where you can break the structure there?
The ring.
The ring, yeah. So what do you get in this particular case? An alkyne, and that's it. So you could imagine having something like this. Anybody knows, or everybody knows what the box group, the Vitoxy carbonate? So you have something like this H. So that's the third Vitoxy, this is the T-box. Protecting group. So typically can be put on from the anhydride. The bottom hydride, carbonate hydride. So you would put it on starting with something more common. And this falls off, T1 group falls off with acid. So you treat this with TFA, typically trifluoroacetic acid, and your protection. So this group is very commonly used in organisms.
So only protected means?
Now it is also used to protect alcohols, and then to protect amides in my bonds. It's very common in different contexts. But the point is how to take it off with TFA, so trifluoroacetic acid. So in this particular case, right, and then for instance, you can start envisioning how you would get to something like this. The way I have it is something that looks like that, right? Basically, how do you put an A side? This is like you cover, right? So we have a leading group, sodium A side, DMSO, polar electronic. That typically you do the trick. In this case, this would just come from NH2, right? So methylate or protect, put your bond group and do an esterification, right? So you can just methylate your acid. Right? We already know of a very mild way to methylate your carboxylic acid, which is, but Fischer is not going to be very mild, and it typically does require acid. But we cover one that is very, very mild. Diazomethane, right? So CH, with a very mild base, you will methylate, and then you can put the bulk group on with your anti-evoking. So that would be the case, and then how you put the bromine, well, you know, and then how you get to this one in this particular case. There is something called homologation, where if you start from an aldehyde, you can go from an aldehyde to the alkyne. We're going to go into those types of processes soon. That's certainly something that hasn't been covered. But again, there are several symptoms that can be used to get an alkyne. In this case, I think what I have is something like, There you go. You have a living room here. So a protected alcohol, and then if you have a living group, you can do addition. You can do also homologation. We haven't learned that, but we will in some cases. So if you start from an aldehyde here, then that would be the idea. Or, so this is one, this is basically what I just came up with. So you put a living group, sterified in each bulk. You can get from here to there. So the point here is that you can have several strategies. There is not one right answer. So you can get to this type of symptoms from different groups. All right. Well, that's the basic idea on the retrosynthetic analysis. If you have something that is more complex, or if you have a target where there is more complex or more. Sometimes, in this case, you're building up on complexity. There are other cases in which you are going to have to start with something more complex and simplify. Right? Well, those are the two common ones. You count that distinction. Are there any questions?
Okay. So how can the T box replace the
How can the T-walk, or how you go from here to here?
Yeah.
That's typically done with anhydride. The T-walk anhydride in the place of potassium carbonate. There are some DCC couplings, and DCC coupling will also work. If you have a DCC and the T-walk anhydride, you can get to the. So you would treat this with DCC and the T-walk anhydride, and that goes. That's So we have DCC coupling. That's the most common one. Okay. Any other questions? All right, so let's look at one more strategy. If you see commonly used, and it's not exactly this, this starts from basically a wide rep amine. So wide rep, how do you generate a wide rep amine? What is it used for? So these you'll see oftentimes. Okay, so if you start from an acid chloride, you can also start from a ester. In these cases, you treat it with HCl salt. And you can do your water like that. That's basically the idea. We'll go into that. Or if you start from an ester, you can also treat it with basically the linear of your meat. Then you get to your corresponding wine rub. Now, the wine rub are very commonly used to make these electrophilic, this carbonyl electrophilic. Basically make additions onto this carbon. In this case, you're getting an acid chloride to the corresponding wine amide, or the ester to the corresponding wine amide. So in this particular case, if you treat with lithium, so that's if criterion with the secondary lithium in this particular case. Let's just look at what I have here. Okay, so criterion with that. You go through this type of intermediate. So essentially, the MU lithium is attacking, or this is dictated or is through this complex. So the lithium ions are known, lithium cations are known to make stable complexes with oxygens. So that's one thing. Whenever you're using LDA, lithium HNDS, particularly in carbonyl chemistry, you're always generating these big clathrates of lithium complexing with whether it's a carbonyl, right, an enolate, or other type of heteroatoms such as nitrogen and oxygen within the molecule. In this particular case, this is stabilized like this. So the oxygens may be complex first to the lithium, and they facilitate the delivery of your nucleophile to the carbonyl. So, of course, in this particular series, what you end up with is right, so then the mechanism you can just envision it in this case, this comes back and it kicks out this. So it's functioning basically as your acid chloride, as your OR, or as your ester in this particular case. But the big advantage, and this is often sometimes used with this type of amide bonds, can be used if you have stereochemistry. So if you are a chiral group, right, you can impart chirality on this type of complex and dictate whether your nucleophile attacks from one phase or the other. So these are some strategies that are commonly used to get to this particular case. Now, in this case, it didn't matter because the structure is very simple. But if you have a stereocenter on this side, that might dictate the stereochemistry, so you might prefer the addition to certain sites. But very commonly used to get the nucleophilicity, the electrophilicity of this carbonyl, and then you have a nucleophile adding on to there. So again, this is going to be your leading group. Then you get your ketone in this particular case. Are there any questions? So one remember this type of strategy. So whenever you see something that looks along these lines, right? In this case, it's useful because we haven't seen, for instance, how you transform an ester to all the way to the ketone. That's a common. Acid chloride, you can perhaps you see it with terbium lithium, right? You get actually double addition. Right? So if you treat this with heavy lithium, what do you get? You get the alcohol, right? So you get first addition, and then another heavy lithium attacks. And that's going to be sometimes hard to control. So in this case, you do it under much milder conditions. Right? So that's the idea. Are there any questions on this? No? Alright, so I think that, let me see, cover fields out there for the exam. Do you know it's a novel reaction? Yes. And I think let's just leave it at this. So up to here is basically what the exam is going to cover. Besides all the things that we've covered, whether are any examples or literature, I'm going to post some references tonight, hopefully, so that just kind of like a study guide or practice. Right? No questions? Follow the problem. Hopefully you didn't make any mistakes, but I can give you the reference at some point. Let me write the reference first. This is Jax. Girl, American Society, 2009, 131, 6674, 6675. That's a good. Okay. Yeah, you can set it. You do this with else select right, what happens? What's else select right? That's your triennial or hydrate. Right, so at that point, it already gives you an idea of what that's going to do. Let's select right. Yeah, sorry, the other one had too many carbons. Didn't make sense. Here is chloride, metazone. What do you get? This orange.
What's the substitution on benzene ring?
Which one? Oimi. Yeah, that's a really kind of computer was indicated. I went to just read this cover. Case. So far, it's pretty straightforward, right? If you look at the transformations. So this one is where it starts getting, it's also relatively straightforward. Transformation, we have seen it in some ways, but not. Okay, everybody has the reference down? If you have a computer, it's certainly maybe easier to just open it. If you don't, this is the sequence. And then certainly we're just going to talk about some steps right now. And I want to ask you to just look over it in detail. Later at home, right? So we just want to go over some of the transformations and make sure that everything makes sense and we're all on the same page. And then you just do the solvents. Check. Again, this is 88%. You can also calculate the total yield. Either solve DCM. The chloromethane is just a solvent, 87%. The hydrogenation reaction should be close to quantitative, 96%. Oxidation is at minus 10 degrees Celsius. This is 67%. Exchange followed by this. This is good. This is DMF. 88%. We got through these points.
So that's a PHE above 88%.
Okay, where?
I'm sorry, just above 88%.
DMF. The methyl formula. It's just salt. Polar ecrotic solvent. Okay, we do this. I'm just gonna go the way there for. This 78 degrees Celsius. We treat it with good. missing here? It looks a little bit more intimidating than what it actually is. Once you start analyzing it, it's more straightforward. Yeah, I guarantee you that. It's taking me actually longer to do it. Yeah, I don't know what happened.
Just call open R.
No. No, because it's all like the changes are very like it's not that big anymore. Just taking oh, I can put the yield here. Yield here is 79%. Let's get a 93.7 DR. Here they get, in the first step, I put 9 to 1 DR. Everyone knows what DR means? The stereomeric ratio. Right? So remember, you have no difference between enantiomers, diastereomers. So how many stereocenters does the molecule have at this point? And which they're called a 9 to 1 DR. How many stereocenters? A lot. Right? 1, 2, 3, 4, 5. 5 stereocenters. How many possible stereoisomers? Right? And so then the idea here is that what is the transformation here? Let's just talk about that. The carbonyl is reduced to the corresponding alcohol, and they get a 9 to 1 stereomeric ratio because they probably get the not probably they get in 10% the opposite diastereomer. At this particular case. So if the molecule varies at one stereocenter, it's a diastereomer. Right? Because all the other then the configuration at each doesn't change here. It only changes at one point. The relationship is that they are diastereomers, right? So therefore, that's what that means. The DR 9 to 1 diastereomeric ratio, and that's how they get in this particular case. So in this other case, they have another one that have 93 to 7, so pretty good diastereomeric ratio. Right, so how are they getting? Now in that particular case, I should say the following is that maybe I should memorize the case. In this particular case, it's here. Otherwise, it doesn't make sense, right? Okay, so let's continue with this. Okay, and I really think you guys can do the other ones, but let's just stop here for now. Okay, so So I would say that if you were to see this on the exam, I think all of it would be fair game, except for this case. This one is a little bit something we haven't seen, but you can certainly propose a mechanism on this to get to here. This is just the oxidized version of a phenol. But let's go on. So is everyone done, or does everyone have the paper somewhere? Certainly, don't forget to get the reference. All right. So as we said, in this case, right, it's a reduction. So LC electride. We haven't seen what LC electride is. You may have seen it elsewhere, but as soon as you see the structure, the borohydride, you see it is a reduction. So even if you, so what other ways could you have used to drive this transformation that we know? LAH would be pretty rough. I think you would start getting rid of benzene groups and some of these things. So for LAH would certainly work. Sodium borohydride would work. So for the class, certainly if you had put LAH in this case, I think that would be okay, because I don't think it would be expected that a benzene group in this case would follow. So that's the transformation here. So what about in this particular case? And this you could propose a mechanism now that you know the structure of LC electride. Right? So that would be, so in this case, it's a protecting group. You know the structure of TBS or TBDMS, the presence of imidazole. Imidazole is a base. So this.
My only question for that is, why did it selectively attack the alcohol group on the top and not the one next to it?
Yeah, it has to be probably steric hindrance in this particular case. They're both secondary. Where am I? Okay. So they're both secondary, but you could argue, perhaps, you would have to build a model.
Yeah.
But it seems to me like this is closer to this big group, and that may be dictating why this happens. So they probably did it slowly, one equivalently, and then that's how they tried it.
Okay.
And the yield is good, so that's definitely the first side. Yeah. All right. So what's the next step? Hydrogenation. Remember, you guys know is this a hydrogenation or hydrogenolysis? Here that means for it's a hydrogenolysis. Why is it a hydrogenolysis? Because you're breaking the bond. Remember, what's the structure of the benzene group? While you're breaking the bond, you get toluene out, and then you gain an OH. So it's a hydrogenolysis reaction. So that's hydrogen palladium. I guess they don't have the solvent or anything that this dissolves in. You just create the hydrogen catalyst, and it's going to. Okay, so what's next? What is the transformation here? It is, the alcohol is oxidized, so the whole phenol is oxidized. What else is going on? Esterification, not really. What is esterification?
And alkoxy group is added.
Alkoxy, so methoxy. So here is your methanol. So it's poison. So where is that coming from? So methanol. Right, so then can you propose a mechanism? You can. One thing you have to consider in all of these cases is that iodine is polyvalent, so it can hold on to 1, 2, 3, 4, 5 bonds. They can come on and off. So that's one thing with iodine. And so in the first step, for instance, in this particular case, that's the idea. So in in the first step, you can imagine maybe that this can attack there. This maybe. All right. You guys can do that. That's the blue there. I'll give you some time if we finish. As I would start with something, of course I immediately tell it, but I would start with something like this to get it oxidized again. You're using a hydrogen, what's attacking, you have methanol, that's going to be probably the nucleophile. How is this transformation occurring? So what about the next step? So what's going on here? Yeah, the alcohol is getting benzylated, right? Benzyl, so it's a benzyl. So how does that, can you draw the mechanism for that? Yes, so sodium hydride, you know what sodium hydride does, right? It's going to the protonate. And then you add your benzyl bromide. But I guarantee you, if you add benzyl bromide, it's not going to work. And that's the reason they have TBAI. So you have to, if you are going to draw this mechanism, you have to consider TBAI. TBAI is basically tetrabutyl ammonium iodide. And that enters the cycle. So it's not going to be a typical reaction. It's going to be a typical SN2. It's just not going to be on benzyl bromide. There's going to be an exchange first. And that's why, right, DMF is your solvent. Or you have to add TBAI. So do that mechanism and make sure you take that into consideration. And so what about here in this particular case? So what's the transformation? I mean, we certainly have not seen anything like this. But what if you look at the change, you should be able to tell immediately how this is reacting and what this is reminiscent to, or what this reminds you of. Which is what? Right, so you just go look at the transformation here. You have your allele. Allele with zinc, and then so what's the transformation is going from here to here? Is that you're basically adding an allele group onto the carbon. So how would you do that? You want to attack your carbonyl. With a Grignard, maybe. So if you use a Grignard, you can certainly attack your MGBR. This can add onto the carbonyl. Now, two things that are occurring here. So why aren't they using a typical Grignard? It's not stereospecific. That's one. What could be another option? Have you guys seen, or does this remind you of zinc bromide? So oftentimes you can exchange, instead of magnesium, you can make the Grignard with zinc. That decreases the electrophilicity. So you have a smoother attack onto the carbonyl, so that you don't start attacking other carbons, right? Or maybe even doing an SN2 or an E2 on a chlorine. That was the idea. So the stereospecificity is covered by this group, and then nucleophilicity is covered by having the zinc there. So you just remember that Grignards can also be prepared from zinc bromide. Then that would be the idea here. Right? So then basically your allele is being delivered to your carbonyl. Then what happens next? In this particular case, you inform your carbonyl. So what else? The allele is shifting, and let me notice the chemistry here that I just noticed Yeah, so the allyl group is shifting from one carbon to, I'm drawing the structure incorrect. No, this is correct. Correct. So this you can do, just look at last class. That's I'm not gonna say too much about it. If you read the paper, they'll probably tell you. This is not like an oxycode rearrangement. Oxycode rearrangement is essentially like a Johnson-Gleason rearrangement, essentially like a 3-3 symmetropic shift. Right, so to do a 3-3 symmetropic shift, you should be able to get it. Now, one thing is, what are they using here to promote the 3-3 symmetropic shift? For the oxycode, it's an oxycode because it's from an alcohol you end up with a carbon. The oxycode would typically be this way. But it's an oxycode type rearrangement, so 3-3 symmetropic shift. In this case, so what is terbutoxide and what's 18 crown 6? You guys remember? No? You guys did cover it. This was covered now. Okay, let me recap. 18 crown 6 is 18 crown ether. It looks like this. That is not 18 crown 6, it's 6 oxygens. That's 12 crown 4. It's going to be this 1, 2, 3, 4, 5, 6. This 18 crown 6. The other one I drew is 12 crown 4. Yeah.
So the carbon that's next, so the allele changes, and then that carbon loses a double bond, like go 1 over. I don't know where to point to it. So the alleles on that first carbon, and then the carbon right next to it, there you go. That one loses a double bond, so is it gaining the hydrogen then, so it's not negatively charged? Or?
Yeah, if you do the mechanism, and you'll see how this occurs.
Okay.
Yeah, but it's, you can do it actually without, but this promotes it more. Just do your 3-3, so remember 1, 2, 3, 1, 2, 3. Okay. That's your 3-3 symmetropic shift. So if you just number them, and then look at your model, right, for 3-3 symmetropic shift. So again, 1, 2, 3, 1, 2, 3. For then you know which bonds are being connected, which is being broken. What do you end up with that is? Because yeah, you're right. You are not forming the double bond. You typically need 2 double bonds there, but you actually do have the double bond, which is right here.
Okay.
So you can always go back. But yeah, so once you do it, I think it will become clear. Okay. So 18 crown 6. That's 18 crown 6. What are the crown ethers? This is part of a family called crown ethers. So it's basically 18 atoms around the crown with 6 oxygens. So if you do 12 crown 4, that's another common one. You have so 12 atoms and 4 oxygens. So 18 crown 6 and 12 crown 4 are used to increase the reactivity of some anions. So for instance, these are known, 18 crown 6 in specific is known to grab onto sodium very selectively. So in this particular case, and potassium. So they have potassium terbutoxide. So what that's doing is the 18 crown 6 grabs onto the potassium very strongly and then increases the reactivity of your terbutoxide. You can see it as an apion ion. So your terbutoxide now is not associated with the potassium, so the 18 crown 6 complexes with the potassium, and now you have your terbutoxide increased, the reactivity is increased. And this is very common, so sometimes if your SN2 reaction is not working, you can One alternative is go to 18 crown 6. 18 crown 6 grabs potassium, sodium. 12 crown 4 is a smaller crown, likes lithium. So you have a lithium base or lithium nucleophile, you add 12 crown 4, and that can complex to the lithium, and you increase the nucleophilicity of your nucleophile. In this case, terpitoxin. Does that make sense? So that's what the crowns, these crown ethers are used for. Yeah.
So after your crown or 18 crown 6 takes the plastic, what is your
Yeah, it's working. See if you can. I think you can do the mechanism without it. For multi-level or something. So, yeah, see if you can figure it out. If you have like I think you can certainly do the mechanism without it. But, yeah, see if you can propose. What? But start like it's a 3-3 sigma tropic. That's the limit. And then, yeah, why is they even have to add 18 crown 6, right? Which is not that cheap. So they added it because that's probably the only way they got it. So can you propose a mechanism? Can you propose? So why is it that they added have to add 18 crown 6? Can you do the mechanism, the oxy-covalent arrangement without base? If you can, then the question is really okay. So why is it necessary? Is that clear? Yeah, so that's a good question, and hopefully as you go the mechanism, you can propose it. Okay, so what's next here? So again, start by looking at the transformation, and certainly look at the reagents. If you look at the reagents, they look kind of familiar, but not really. I mean, look at the transformation, and then go back, and then so what's going on here? Ozonolysis, O3, right? You know it's ozonolysis. So what is ozonolysis? Have you ever seen this type of reaction or workups? You've seen this workup? Typically what it's taught, what I teach in the organic chemistry course is you do ozonolysis is reductive workup or oxidative workup. Reductive workup is you add zinc or DMS, right? What is or PPH3. Those are your three, or the three most commonly reductive workups. If you do oxidative workup, it's typically H2O2 and some other, right, for ozonolysis. So in this case, it's certainly ozonolysis. So you stick by the non. So what does ozonolysis do? Yeah, breaks the carbon-carbon bond onto the carbonyl. And then what? So in this case, you have 1, 2, 3 carbons. You end up with 1, 2 carbons, and then an N. So you go on to, so is this going to be, without knowing what this workup is it reductive or oxidative? Probably. Oxidative, so that would mean you cleave it and you end up with a carboxylic acid? Yeah, I don't know if it's a pyridine, but I personally had, or do not remember, or have, this is not a common stage. But as soon as you see it, I have to say that without going into the mechanism, that it has to be reductive. Why is it reductive? Because in the next step, they have an amine. An amine, you know, it can react with an aldehyde. It's not going to react with a carboxylic acid. Furthermore, you have sodium cyanoborohydride. And sodium cyanoborohydride, you know that it does what? Reduces typically imines. So that tells you that probably you're forming an imine from an aldehyde, reducing the imine, and that's how you get this. And this is your methyl from here. Right? So sodium cyanoborohydride. This, if you haven't seen before, I mean, it doesn't matter, right? At this point, you already solved your problem. So this is just molecular sieves to get rid of some of the water that's generated in the process of making the aldehyde. But remember, forming an imine, it's an acid-base reaction that it's reversible. So then by getting rid of water with the molecular sieves, you're driving the equilibrium towards the aldehyde, that then can be reduced with sodium cyanohydride. All right, are there any questions with this?
I just have one.
Yes.
So for, as far as like linear synthesis goes, like when there's two steps, for a reaction, do you count each of those as A and B or just the products for each of the reactions?
For this linear one,
Yeah.
if is what? How many
So
steps?
if there's like two steps, you see like when we have like one and two,
Two.
no, like way down. Yeah,
Oh,
the weight
analysis.
analysis, like that's just one.
This is
product.
54, well, this is 54% of the two steps.
Okay, so it's already been like.
I mean, I don't know, I didn't check if they did it. They must have done it on the same pot.
Yeah.
I don't think so. Maybe they just didn't do a column or anything and they just went directly.
Okay.
So it might be one step, but this implies that you certainly have to do it in two steps. So you cannot use
No, you can't.
just
do
create
that.
ozone in the presence of these two.
Yeah. Okay.
I think it's very clear. So you would say one step, but this one step is actually two steps. Mechanistic. Right? Okay. So certainly look this paper up. I think it's going to good practice. Next, bring questions next time in preparation for the midterm. And then next time, what I'll do is we'll start talking about presentations. I'm still trying to figure out what's gonna work.
So, did you say there was going to be some retro synthetic on the exam?
What was that?
Yeah, perhaps it's not